Hello and welcome to our webinar. My name is Vladimir Padnos. I'm Director of Marketing and Support here at Terra Analysis Limited, and together with my colleague Alexander Lubimtsov, our support engineer, we will discuss stress analysis simulations with QuickField. QuickField is multiphysical finite element package, and on this slide you see a set of analysis options available today. They include magnetic analysis with magnetostatics, AC magnetics, and transient magnetic, electric analysis including electrostatic, DC conduction, AC conduction, and transient electric field analysis, and thermostructural family of packages for steady-state heat transfer, transient heat transfer, and stress analysis. Today we will discuss stress, and stress analysis model allow to simulate plane stress and strain, axisymmetrical stress problems, including anisotropic, orthotropic elastic properties. It allows various types of loads, thermal stresses, various support conditions, and post-processor shows results as displacement, stress components, principal stresses, and various failure criteria. Most important, what QuickField is a multiphysical package, and stress may be calculated not as a pure mechanical problem, but as a result of complicated multiphysical analysis. We could transfer forces calculated in electromagnetic part of package. We could take into account temperature distribution and thermal loads calculated in the thermal models, and all this makes stress final part of complicated magnetostructural or thermostructural analysis. It is also important to know what QuickField features not only very developed user interface, but also application programming interface, which allows combining of QuickField functions with external models. Programs and scripts written in different languages and programming systems may interact with QuickField core through application interface called ActiveField. And this allows us to take into account change of geometry, displacements calculated in the stress model, and bring this back to modify the settings for thermal or electromagnetic problems. So this loop of couplings may be closed using ActiveField programming. And unlike many other stress analysis systems available today, QuickField doesn't require much of effort from end user. It is a very simple package, and I believe following the presentation of my colleague Alex, you will understand what QuickField is a very convenient tool for various applications, and many of stress problems may be solved with it. Now I will ask Alex to continue.
The first case is the simulation of cylindrical rod under mechanical stress. The cylindrical rod is made of aluminum alloy. It has length of 3 meters and the cross-section diameter of 30 millimeters. The force of 85 kilonewtons is applied to the rod end and directed along the rod. And our task is to calculate the rod elongation. I will start from sketch so we can see all the steps. So I start QuickField and will create the new problem. I should specify the problem name and the location folder. Then I should specify the problem type. the stress analysis, and the model class. I will choose the axisymmetric model class, which is suitable to simulate the cylindrical objects. Now here is the problem tree, and you can see the geometry model editor window. Here I should draw the geometry model. So the rod length is 3 meters. And its diameter is 30 millimeters, so I simply duplicate this. This is the cross-section of the rod, and I draw only the upper half of the cross-section. The horizontal axis, this one, is the axis of rotation. Now I should assign the labels to every geometric object. This is the axis. This is the aluminum. I will have this and fix it. And I will apply the force to this end. On the next step, I should specify the physical properties to each of the object. So for the axis I specify zero displacement in radial direction. For the fixed end of the rod, I specify zero displacement in z direction, and I should apply the force. You see, instead of newtons, I should specify the force, the surface force, or the force density, which is calculated as force divided by the cross-section area. QuickField allows you to specify not only values but also the formulas, so I will type in here the formula, the force divided by the cross-section area, which is P multiplied by the diameter square divided by 4. And I should specify the physical properties for the aluminum. Now the Young's modulus of the aluminum is 70 gigapascals. And the coefficient here is 1/3. Now I have the geometry model ready, and I have all the objects described. The last step is to build the finite element mesh. I will zoom in to show you that the mesh was built in fact. Now I should save all problem files and run the simulation. After the problem is solved, you can see the results. You can see actually the deformed shape and the boundary of the rod and the color map of the failure criteria. Let's switch on the color map of the displacement. You may note that this deformed shape is scaled, so we can see the shape on the screen. In fact, if we set the scale to 1, we will hardly see any change because the maximum displacement is only 5 millimeters. Now we can see the color map of the displacement. And this is the displacement, the deformed boundary. We can also switch the vectors of displacement, and we can switch on the color, for example, the principal stress color map. The vectors denotes the direction of the displacement, and the green color denotes the stress distribution, the stress in the rod. You may note that the stress distribution is uniform because we have the same cross section along the rod. Now back to our task. The rod elongation is, I will click this point, and the displacement of this point is 5 millimeters. This is the perforated plate under the mechanical stress. In the previous case, we got the uniform stress distribution, and now we have the thin metal plate with the hole, and the hole is the source of the stress concentration. The plate has thickness of 5 millimeters, and the force is applied here on the top edge. The bottom edge is fixed, and our task is to calculate the stress distribution in the plate. Again, for this simple case, I will start from the scratch and show you all the steps. So I start QuickField and create the new problem. I specify the problem name and the location folder. Here I specify the problem type, the stress analysis, and the model class. It's the plane parallel. I should also specify the thickness 5 millimeters, and I should choose the formulation. If you refer to QuickField help, theoretical description part, the stress analysis formulations, you may note that there are two formulations. The plane stress model is suitable for analyzing thin structures, and the plane strain model is used for thick structures, assuming that out-of-plane strains are negligible. So for my thin plate, I should choose the plane stress model. Now here you can see again the problem window and the geometry model editor window. Here I should draw the geometry model. I will check the dimensions. 180 millimeters by 240 millimeters. Now this is the plate, and I should draw the hole inside. Now it has the radius of 30 millimeters. Now this is the geometry model. Again, I should assign the label for each geometric object. This is the plate. This is the bottom. And this is the top. Now I should specify material properties for each object. The Young's modulus is 20.7 gigapascals. And the coefficient here is 0.3. The bottom side is fixed. And on the top side, the force is applied. The force density is 40 Newton per millimeter square. So it is minus 40 newtons 10 to the power of 6 per meter square. Now everything is ready. I can build the mesh, save all simulation files, and run the simulation. From time to time you can saw the warning message, not enough boundary conditions. We have not fixed the plate in horizontal direction, so there is an ambiguity in plate position. It could be easily fixed. The model features the horizontal symmetry, so we can add the symmetry axis, give it the name, and specify that the displacement, the horizontal displacement, is 0 on the symmetry axis. Now we have fixed the plate in horizontal direction. We fixed the plate at the bottom in vertical direction. We can build the mesh and run the simulation. And here you can see the results. The results present the deformed form of the plate. Let's adjust the picture settings. We can see that actually the deformed shape display is scaled by the factor of 3000. It is done so we can see the change in the shape on the screen. If we change the scale factor to 1, then we will not see the deformation on the screen because the deformation effect is very small value. The maximum displacement value is only 5/6 of the millimeter. The 6/10 of the millimeter. So if we will change the scale to 1, we would see nothing. So right now on your screen you can see the color map of the displacement. But we are interested in the stress distribution. So I will switch off the deformed shape and switch on the color map of this principal stress. You can see indeed the hole in the plate causes the stress concentration here and here. And we can see not only the color map, the value of the stress, but also the direction of the stress. I will switch on the tensors and will adjust the scale so you can see better. Now you can see the value of the stress and the direction of the stress. You can see in most part it is compressing stress because we push here, push down here, but in some parts, due to the concentration caused by the hole, we have the elongation stress. The mechanical force could be of different kind, and in this example we will simulate the force caused by the electric current interaction. Here is the long solenoid carrying electric current. This is the winding. You can see the cross-section of the solenoid. And our task is to calculate the stress distribution in the solenoid. The current interaction, if we take a look at the single lobe of the solenoid, the current interaction is ruled by the Ampere's force law. In short, the force is in direct proportion to the currents product and in inverse proportion to the distance between the currents elements. And the best way to calculate the magnetic force is to perform the magnetic analysis. So I will start QuickField. Let me show you the problem properties. This is the magnetostatics problem, and the model class is axisymmetric. Axisymmetric means that we will simulate only the upper half of the cross section, and this would be the axis of the rotation. Now this is the geometry model. It's a small portion of the very long solenoid. So in fact this is only the small part. Here we have the two blocks, the coil, and the coil is carrying the electric current. And we have the air block. And the result of the magnetic simulation is the magnetic field distribution. I will switch on the column map of the flux density and the vectors of the flux density. So we can have the magnetic field, we have the electric current, and there is the magnetic force acting on the current elements. And we can measure this force if we select the coil if we select some element, some current, and follow to the integral, we can calculate the mechanical force acting on this element. So naturally our next task is to calculate the stress distribution in the solenoid. To calculate the stress distribution, I need the stress analysis problem. So I will create the new problem and call it stress. I should choose the problem type, the stress analysis, and I should choose the model class, the axisymmetric. Now I would like to automatically transfer the forces from magnetic to stress analysis problem. To do so, I should choose the same geometry model in both problems. So in stress analysis problem, I will use the geometry model, the same geometry model that I used in magnetostatic analysis. Couple 1. Now both problems share the same geometry model. And in this case, I can set up the link from magnetic to stress analysis problem. So I follow the stress analysis problem, open the problem properties, and follow to the links. Here I specify the link type, the magnetic forces. I choose the problem that contains the magnetic analysis result, this problem, and I add the link. Now my stress analysis problem is linked to the magnetic problem and imports magnetic force from the magnetic problem. Don't forget to specify material properties. In magnetic problem, we specified magnetic properties of the coil, and in the stress analysis problem, we should specify the mechanical properties of the coil. The Young's modulus is 107 and 5. Gigapascals, and this coefficient is 0.33. I will not calculate the stress distribution in the air, so I simply open the block properties and specify nothing here. I have a very long solenoid, so there is no axial displacement, because this same part present here and here on the left and on the right. So no axial displacement here. Now let's simulate the mechanical problem. Here you can see the results. I will zoom out so you can understand better. This was the original cross-section of the solenoid, and this is the deformed shape of the solenoid winding. Again, I can adjust the field picture and switch on the stress distribution color map and the vectors of displacement. So you can see the winding is pushed outside by the magnetic forces caused by the current flowing in the winding. Let's move to the next example where the mechanical force is caused by the thermal expansion. This is the gas pipe that contains the gas under pressure, and the gas has the temperature of 100 degrees Celsius, while the outside area has the temperature of 0 Celsius. The internal pressure of the gas is 1 megapascals. Our task is to calculate the stress distribution in the pipe caused by the thermal expansion and the internal pressure of the gas. Again, let's start QuickField. To calculate the temperature distribution, naturally we need to simulate heat transfer problem. And to calculate the stress analysis, we need to simulate stress analysis problem. So there should be two problems here. One is the thermal problem to calculate the temperature distribution, and the second is the stress analysis problem to calculate the stress distribution. Heat transfer and stress analysis. In fact, there are two ways you can simulate this case. You can run the you can do the axisymmetric model and simulate the upper half of the cross section, or you can take a look from the side at our pipe and simulate the plane parallel case. I will show you both. So this is the heat transfer problem. You can see this is the cross section of the pipe. In fact, the pipe is very long and I have only the small part of the pipe present in my model. This is the thermal problem, so for each object I should specify the thermal properties. And on the edge, I specify the temperature. On the inner edge I have 100 degrees Celsius. And on the outer edge I have 0 degrees Celsius. And on the side edge I have 0 heat flux, because there is the same pipe on the left and the same pipe on the right. Now let's take a look at the simulation result. You can see the temperature distribution in the pipe. And to calculate the stress distribution, I need the stress analysis problem. To have the problem coupled, the stress analysis problem use this same geometry model. So when creating the stress analysis problem here, I manually specify the geometry model file from the heat transfer problem. Also, I have specified the link, so the temperature field will be imported from the heat transfer problem to the stress analysis. To specify the link, I open the Link tab, choose the data type, found the source problem, this one, and then press the Add button to add the link. Now let's take a look at the simulation result. One moment more. In stress analysis, you should specify the mechanical properties for each object. Here you can see the mechanical properties of the pipe. And you should follow to the load step and specify the thermal expansion coefficient, so you will be able to simulate the thermal stress. And the reference temperature will be imported from the heat transfer problem. Now let's take a look at the simulation result. Again, you can see the deformed shape. The deformation is caused by the thermal expansion and by the internal pressure. I will switch on the color map to see the displacement. Now that was the axisymmetric formulation. But the same problem could be simulated as the plane parallel if we take a look from the side. Let me show you. This is the side view of our pipe. Again, this is the cylinder, and in thermal problem I specify the thermal properties for each object. Inside I have the temperature of 100 degrees Celsius, and outside I have the temperature of 0 degrees Celsius. And again I added the symmetry X and symmetry Y axis, so we will be able to fix our pipe in stress analysis problem. Let's take a look at the result. This is the temperature distribution in the pipe. The same temperature distribution we saw in the axisymmetric case. We saw only this small portion of the model. Now let's open the stress analysis problem. Again, the stress analysis problem shared the same geometry model with the heat transfer problem, and this allows us to set the link and automatically import the temperature field from heat transfer to stress analysis. Now let's take a look at the result. This is the deformed shape of the pipe caused both by the internal pressure and the thermal expansion. And I will switch on the displacement. Now let's compare the simulation results of both problems. The plane formulation and the axisymmetrical formulation. You can see that the results are pretty much the same. So this way you can verify calculation. And this corresponds to the small part. This is the Bimetallic thermal control unit. There are two electrodes, the base electrode and the magnesium electrode. There is a small gap between the electrodes, and our task is to calculate the temperature increase at which the two bars came into contact. I will start QuickField and open the simulation case. This is the stress analysis problem. I have two plates, the brass plate and the magnesium plate. For each plate I specify the mechanical properties and the thermal expansion coefficient. And my task is to find at which temperature the two bars came into contact. Left and the right are fixed. And we can solve the problem at 0 ref temperature. Now there is no elongation, there is no stress nor strain, because we have 0 temperature and the bars are not in contact yet. Now if I will rise the temperature, for example 20 degrees, and will adjust the field picture and switch on the displacement. Please note that this is the scaled form. If we adjust the scale factor, we can see that the bars in fact is not in contact. So I should increase the temperature. I increase the temperature both for the brass and for the magnesium plates and solve the problem again. And again I will look at the deformed boundary at scale 1. And again, this is not the temperature when the plates came into contact. So what should I do? I should again increase the temperature and solve the problem. In fact, you can automate these tasks. We have the label mover tool, which allows to automate the calculations. What I need now is to perform the serial analysis. So first of all, I choose the base problem. thermal control. Then I specify that I would like to perform the serial analysis. I should also specify the steps. What values should I change during the simulation? I will change the properties. I will change the reference temperature. I will increase it by 10 degrees. In one step, I will increase the temperature of the brass and of the magnesium bars. And I would like to repeat this step, say 10 times. Next, I should specify the values to measure. In my model, I have the two reference points. The left point and the right point. I will measure the coordinates of each, the displacement of each of the point, and when the total displacement will be equal to the air gap, then I will know that my plates came into contact. So for the measured values, I would like the displacement in x direction for the left and displacement in x direction for the right. Now everything is ready. I have the base problem specified. Here it is. I specified which steps to perform and how many steps to repeat. And I specified values to measure. Now we can run the analysis. I press the Get Result button. You see the problems are generated. Then QuickField simulates each problem and calculate the displacement. And the results are stored here. Now everything is ready. I will copy the results to Excel file to perform the analysis. Now I started at 40 degrees and increased the temperature by 10. So this is the temperature, and this is the left, this is the right. And this is the total displacement. So the A gap is 5,000th of the inch. So somewhere here between 100 and 110 degrees, the plates will come into contact. Again, this is the solenoid example, and let's consider the wiring process. The winding force leads to wire elongation, And after the force is removed, the wire shrinks and squeezes the bobbin. And our task is to calculate the bobbin deformation. Relative elongation of the wire according to the Hooke's law is described by this formula, where F is the force, E is the Young's modulus in pascals, and A is the cross-section of the wire. L0 is the initial length of the wire. And the similar effect of a shrinking wire may be achieved by cooling down the loose wiring. So if we would have the loose wiring and cool down it, the wire would shrink and squeeze the bobbin. And this effect is ruled by the thermal expansion law. So we can use the thermal expansion effect to simulate the shrink of the wire. All we have to do is to calculate the temperature difference from these two equations and apply this temperature difference to the loose wire to simulate the wire shrink pressure. Let me show you this model. This is the stress analysis problem. And the model class is axisymmetric. In my geometry model, I have the two objects, the bobbin and the wire. And to simulate the force caused by the wire shrink, I will cool down the wire so it will shrink and squeeze the bobbin. Let's take a look at the simulation result. I will switch on the displacement color map. This is what's happened with the bobbin when we wire the winding on it. Here is the model of the inductor. There is the winding, there is the steel core, and there is the air gap in the left and in the right legs. The mechanical force is applied at the point above the right leg, and eventually the core will be deformed. Our task is to calculate the core displacement and to find the effects caused by this displacement on the magnetic flux distribution. So I should start with the stress part. This is the core. And the force is applied here. There is the winding inside the core, and the mechanical properties of the copper winding is specified here. The bottom side is fixed. And there is the air block. The air is used to calculate the magnetic field distribution. There is no mechanical stress in the air block, so I have not specified any properties for the air block. Now let's take a look at the simulation result. You can see the deformed shape. I will switch off the color map. In fact, this shape is scaled by factor 1000. The real displacement value is relatively small, about 1 millimeter. Now we have the tool that allows us to export the deformed shape back to the geometry model. This tool is published on our website. In fact, it is a very simple tool. QuickField features the Open Object Interface, so you can control QuickField not only from the graphical user interface, but from within other programs. So this is the program that will operate the QuickField. So what this program do? It calculates the displacement in each point and then move this point in geometry model. So this way we will have the deformed geometry model. And in the end, the geometry model will be saved with the new model name. Let me show you how it works. It asks us to start QuickField and close all problems and open only the stress analysis problem. So I have the stress analysis problem here. I open the simulation results. Now I can press OK button. You may note that some nodes are moved according to the displacement calculated by the stress analysis simulation. So this tool check each point position and move it to the proper position. When everything is done, we will see the message that the job is done. Now we can save this model as a deformed version of the original model. Now let me show you what this deformation caused. This is the magnetostatics problem, and here this is the original undeformed shape. I have the steel core, I have the primary winding carrying the current, and the result of the magnetic field simulation is the magnetic field distribution in the core. Now let's change the geometry model and choose the deformed version of the geometry model. I will build the mesh and run the simulation again. If you adjust the picture, you may note that there is indeed some asymmetry in the field distribution, because the air gap here is a bit less than the air gap on the left.